Bismillahirrahmanirrahim. Welcome, dear students, to the platform of Quanta Publishers. This is lecture series Teach Yourself, and today our topic is about the resultant vector and the product of vector. In the last lecture, we have seen about the addition of vector and subtraction of vector and some basic terms related to the vectors. And today you see that we are going to discuss about the resultant vector, how we can define it, and how to write the final equation for the resultant vector. Here you can see that resultant vector is the sum of the two or more vectors which have the same effect as the combined effect of all the vectors to be added. Here in this diagram you will see that we take first vector A along this direction and then add this vector b using a head to tail rule in this direction. Then we can attach a third vector using the head to tail rule along this direction, and the fourth vector represented by d can be added using head to tail rule along this direction. Keep it in mind, we can add multiple vectors by using the head to tail rule. At the end, using a head to tail rule, the last vector should be connected from tail to tail and head to head. Here you will see that when we are going to discuss about the resultant vector, the final blue vector over here, you will see that its tail is connected with the tail of first vector and its head is connected with the head of vector. And in mathematical notation, we can write it as resultant vector r on the left hand side is equal to the sum of all the vectors on the right hand side. Here is vector a plus vector b plus vector c, then plus vector d. Now come to the topic about the product of vectors. Can we multiply vectors with each other? Yes. Here are the two parts of product of vectors. We can multiply it in the two methods. One product is known as the scalar product and the other product is known as the vector product. The difference between them is that if we multiply the two vectors and the resultant becomes a scalar quantity, then we can say that the product is a scalar product. And if we multiply the two vectors and the resultant will generate a vector quantity, then this product is known as the vector product. Now we will discuss about the scalar product today. Here you see that the definition of the scalar product. If the product of two vectors results in scalar quantity, then the product is called the scalar product. And this scalar product is also known as the dot product, and it is represented by the dot present between the two vectors. We will see that how to write its mathematical notation. First of all, come to this diagram. You will see over here. Here is a vector A along the x-axis, and there is a vector B along this direction. If we want to resolve this vector B into its perpendicular component, you will see that we take a perpendicular line along this direction and drop it over the x-axis. And now this vector B is resolved into two parts. First vector having a magnitude, you will see over here, that is B cos theta. And the other one you will see over here, that is known as B sin theta. Now these two components will play an important role over here. You will see that this vector B cos theta is along the direction of vector A. So this will play a role in the dot product. whereas the b sine of theta is perpendicular to the vector A, this will not play a role in the dot product. So we will choose b cos theta because it is in the direction of vector A. Mathematically, we can write it as, you will see over here, that A dot B is equal to the magnitude of first vector A, then the magnitude of second vector B, and the trigonometric ratio cos of theta. Because in the above diagram, you will see that the component of vector B, that is b cos theta, is along the direction of vector A. So this will play its role in the dot product. So we will choose cos theta as the trigonometric ratio between the two vectors A and B. Or we can write it as, here you see that the on right hand side vector A magnitude, and we can say that this term b cos theta is the projection of vector B on vector A, because when we resolve vector B into its component, this component b cos theta can be taken as the projection of vector B along the direction of vector A. Or the other way around, we can write it as b dot A. First we choose the vector B, then we take its dot product with the vector A. Then we can write B vector's magnitude and then the projection of vector A along the direction of vector B. Now here we can resolve vector A into its component. So the projection of A in the direction of B can be written as A cos of theta. Here are some examples of the dot product. You will see that the work done can be expressed as the dot product between the two vectors. First vector is the force and the second vector is the displacement. The second example is the dot product between the force and velocity. That is becomes the power. And the third example is the dot product between the electric field intensity E and the vector area A. This is the definition of electric flux. Here are some characteristics related to the dot product, which are, first of one, scalar product is commutative because in the above discussion you will see that A dot B is equal to A B cos of theta and B dot A is equal to B A cos of theta, and the both equation will generate the same result. Both equation will generate the same result. So we can say that A dot B is equal to B dot A. And the second one is the scalar product of the two vectors is maximum when they are parallel. Means the angle formed between the two vectors is 0 degree. And the scalar product is when the angle between the two vector is 180 degree. Using this property, we can place an angle over here. A dot B is equal to AB cos of theta. Now we use theta is equal to 0 degree when these two vectors are parallel to each other. We know that cos 0 is equal to 1. So by replacing its value over here, cos 0 is equal to 1, we will get A and B. So A dot B is equal to AB, and this product is positive, strictly positive. So we can say that the resultant is maximum. On the other hand, if we choose cos theta is equal to 180 degree, then cos 180 is equal to -1. So we can place over here the -1, and this product will become negative, minus A and B. So another maximum, but along with the negative sign. In the terms of unit vector, we can write it as I dot I, j dot j, and k dot k. That becomes equal to 1. Because unit vector has a magnitude is equal to 1, when we can place the magnitude of the first vector, that is equal to 1, then we place the magnitude of second vector, that becomes equal to 1, and cos 0 is also equal to 1. So the final product becomes equal to 1. And the third property, here you see that the scalar product is minimum when they are perpendicular. So here in this equation you will see a dot b is equal to ab cos of theta, and now we choose the angle theta is equal to 90 degree and cos 90 is equal to 0. When we place it over here, the final product will become equal to 0. So we can say that the scalar product vanish when the two vectors are perpendicular to each other. Or in case of unit vector, we can write it as I dot j and j dot k, then k dot I. All these three products will become equal to 0 because these three vectors are mutually perpendicular to each other. We know that x-axis, y-axis, and z-axis are at 90 degree to each other. So when we choose I unit vector and multiply it with the j unit vector along this direction, so the final product will become equal to 0. And the fourth property is the self dot product. When the vector A multiply with itself, then what will be its resultant? Here you see that when vector A is dot with again vector A, then we can replace it the magnitude of vector A, then again the magnitude of vector A and cos of theta. Whereas theta between these two vectors, because it is a self product, so the angle formed between these two vectors is equal to 0. And cos 0 is equal to 1. We can replace it over here, then the magnitude will become a square. So we can say that the self product of two vectors is equal to the square of its magnitude. And the fifth property is the scalar product is distributive with respect to addition. Here you see that if vector A is distribute among the vector B and C, then we can open it on the right hand side as A dot B, means the vector A is distributed first with the vector B, then it is distributed with the vector C plus A dot C. Or on the other way around, we can write it as A plus B dot C. Then this vector C is distributed among the sum of the vector A and B. So we can write as A dot C plus B dot C. And finally, the sixth property is in terms of its rectangular component. In first lecture, we have seen that how to resolve a vector into its components. The vector A in 3 dimension has the three component. We can write it as AXI plus AYJ plus AZK, and the B vector is equal to BXI plus BYJ plus BZK. Here is the BZ, and the unit vector is K. So when we multiply these two vectors A dot B, then we can write it in the form, because we know that if we multiply the vector component Ax, because here is the unit vector I, and in second vector B, here is the component Bxi, because these two components contains the I unit vector, and we know that I dot I is equal to 1, whereas the other components I dot j, j dot k, k dot I, this becomes equal to 0. So we will retain the similar unit vector over here. Here you see that the first component Ax and Bx, because here is the dot product between the two unit vector I dot I, and the second component is Ay By, because here is the dot product is among the unit vector J dot J. And the third component is AZBZ, because here is the dot product among the two unit vector k dot k. Whereas the rest of the product I dot j, j dot k, k dot I, that becomes equal to 0. Thanks. We will meet in the next lecture.